Hello and welcome to the Week 3 Extra Exercises walkthrough video. This week we're going to start off with some theoretical content relating to working with Matlab and programming fundamentals in general, and then for about the halfway point we're looking at some more coding focused exercises. You'll notice as we move through this video that it's actually been stitched together from multiple recording sessions. The only reason for that is we used to be in semester mode with 13 weeks and now we've moved to trimesters with 10 weeks. So when I shuffled around all of our lecture content, extra exercises, I had to shuffle the videos a little bit too. So that's what you're seeing there. But I have set up the chapters on the in the YouTube description to follow along with the task sheet order. So as long as you follow through that order, it all should line up and hopefully be relatively clear. So yep, that's what you'll be seeing there. Enjoy the rest of the video as we work through these solutions.
So we'll start at the start. Question 1 asks, what are the 3 elements of structure theorem? For each element, provide a brief definition and give an example of where it would be useful. So this one is straight out of the lecture notes. If we have a look at the lecture notes on slide 10, it gives us the answer for that. So the 3 elements are sequential processing, conditional processing, and repetitive processing. So let's put those in. So sequential processing, conditional processing, and repetitive processing. Now, sequential processing is where one line of code executes after the other. So one formula gets executed, then the next, then the next. So it goes sort of down the page. Conditional processing is when a particular block of code only runs when a particular condition or conditions are met. So that's like our if statements in Excel. It's where logic comes into it. Repetitive processing is where certain code is executed for a certain, repeatedly, for a certain number of times, or until some, I guess, condition is met or some result, some desired result is obtained. It'll become clearer as we actually get into the different types of repetitive processing. So I've definitely worded it differently there to the notes, but the important thing is that you can explain the overall concept. So the next one asks us to look at a block of code and work out what the values of each of the variables will be. So let's have a look at line 1. At line 1, I'll just sort of write this out. So at line 1, A is being set to 100. At line 2, A is being multiplied by 2 and the result is being saved in A. So in other words, A is being set to 2 times 100, which is 200. In line 3, we're setting B to A minus 3. So B is being set to 200 minus 3. Therefore, B is set to 197. For line 4, C is being set to 200 plus 197. Therefore, C is set to 397. And lastly, in line 5, D is being set to 2 times C. Therefore, D is set to 794. So we can also have a look at this in Matlab to see how it executes. So I've actually got Matlab open. So let's just create a new little script and we'll copy that code in. So I'll just move this over to the window. I'll get this to pop out actually. Doc. So I'll just copy this straight in and I'm going to leave off the semicolons. So when the semicolons are there, it suppresses the output, so nothing prints in the main Matlab screen. If we leave them off, then it actually will print. So if I write A equals 100, A equals A times 2, B equals A minus 3, C equals A plus B, and lastly D equals C times 2, without those semicolons, we should see the output of each of these steps in the main window. We'll need to save this first. I'll just save it on my desktop as week exercise. And then if we go back over to the main window, change folder, we'll see that at the first step, it was equal to 100. Second step, 200, then B was set to 197, C was set to 397, and D was set to 794. Over in the sidebar, we can also see those final values, which match up with what we had expected. Next up is variable naming. So variable naming I want to talk about a little bit because a good variable name is one that's descriptive and reasonably short, but there's also lots of different options for what that might look like. So for example, the first one says a variable that represents the length of car in centimeters. So some obvious ones might be car length or car length with an underscore in between. So that's either camel case or the underscore format. Either one's fine as long as you're consistent. So that is probably fine where the car length is only ever expressed in centimeters. You could define the units in the comments, for example. But if for some reason you've got multiple variables that represent car length, perhaps one in centimeters and one in inches, you might also want to actually include the units. So it might be car length cm in either format. You might even have other ideas like, I don't know, length of car or something like that. There's lots of different options that might be valid variable names as long as they're descriptive and short and include units if the context requires them to. The next one's also a good example of something that can be a bit subjective. So this asks for a variable that represents the cost per month of a Netflix account. So we don't know anything about this program. The program could be looking at entirely Netflix related information, or it could be something that like compares Netflix to Stan to Amazon Prime, all the different streaming services. So depending on the context would help you to determine what the variable name should be. So if the program is entirely about Netflix, you could probably just call it cost per month or monthly cost. And again, you could use camel case or underscore format. But if it's a program that also is comparing like Stan or Amazon Prime, you might actually need to put in the fact that this is the monthly cost for Netflix. So it might be monthly cost Netflix or Netflix monthly cost. There's a number of options for what would make a good descriptive variable name. So there's not really one right answer, as long as it's descriptive and makes sense in the context. The next one asks for a variable that represents a list of all books owned by a library. So that could be books owned. It might be all books. Again, it could be in underscore format instead, whichever you prefer. A variable that stores the street address of a customer for shipping purposes. So again, a couple of options. You could go customer address, you could go shipping address, street address even, just something that's sensible given the context. And again, you could use underscores instead of camel case there. So the next one asks for a variable that represents the conversion factor for conversion between inches and centimeters. So this one's probably going to be something like inches to centimeters. You could abbreviate it to something like into cm, so inches to centimeters. However, that is a little bit less clear, so I would recommend something a little bit more explicit like inches to centimeters. Also, if you're going to use abbreviations, I think that the underscore format looks a little bit nicer than, say, IN capital T. Like that second one just doesn't quite look right, I guess. So yeah, I would suggest writing the full word out, something like that. But if you use abbreviations, perhaps consider using underscores. But again, be consistent throughout your code as to whether you choose underscores or camel case. The last one is a variable that represents a Boolean value that is used to determine whether the oven is on or not, so that once you've left your house, you can check without having to drive home. So Boolean variables, by convention, often start with is, because it's sort of checking a condition, right? Like, is oven on? True or false? So is oven on would be a pretty good one for that. Yeah, so just conventionally often starts with is for Boolean values. So consider using that in your own code. So the next question is about code efficiency. So we're going to have a look at this code for the quadratic equation solver. We did go over this in lectures, but we'll have a look at it again now. So I'm just going to start by copying that all down. So we've got our calculation of discriminant here. And if that's less than 0, then there's not any real solutions. So that's what we put into our little message here. So the disp function prints a message to the main screen of Matlab. So else display there are real solutions, and actually calculate those solutions. So x1 equals negative b plus square root b squared minus 4 times a times c over 2 times a, and x2 equals negative b minus square root, all of the same thing. So type that all out. Now, I asked about the efficiency of this, the reason being that this isn't as efficient as it could be. So if we have a look here, the discriminant is being calculated here to determine whether it's less than 0. And it's also being calculated both here and here. So we're doing that same mathematical operation 3 times, which takes longer than doing it once. So what we can do is we can create a variable called discriminant and set it to the value of b squared minus 4 times a times c. And then we can go through and replace these other occurrences of that mathematical equation. So we can go to here and replace it with discriminant. We can also go to here and replace it with discriminant. And we can go to here and replace it with discriminant. And in doing that, what we do is we calculate that once and we save a little bit of computational time later on. Might not seem overly important for something like this where we're only giving it sort of one set of numbers. But if we were processing 100,000 sets of numbers, then that extra efficiency would add up to a big time saving over that block. So we can run this code now and we'll pop back over to the main window of Matlab. And we can see there's no real solutions for that one. Let's try and change it around a little bit and see if we can find some real solutions. So one combination of numbers that works to give us an actual answer is 1, 10, and 1. So I've just picked a number of b that's a little bit higher rather than continuing to guess around. So here it says there are real solutions and it provides those real solutions. If I change that b back to 1, then we get there are no real solutions again. So it's performing some logic, but it's using this variable to speed up the process because it doesn't have to recalculate that part of the equation every time. So that's the end of that one. Our next one was about writing an if statement. So write code to create a variable number and assign it any numerical value. Let's go through and actually do this along with the steps. So I'm just going to I might shrink it down this way so that we can put it underneath. All right, so I'm going to just get rid of all of this code now. So create a variable number and assign it any value. I'll give it 23. Next, we want to write an if statement that checks if the number is greater than or equal to 0. So if number greater than or equal to 0, the same conditional operators that we've used in Excel. So then we also need an end statement to close that if, so we can put that in straight away. So if the condition is met, we want to display the message, the square root is real, and actually return the square root. So we can do that by using the sqrt function, which is the same as Excel. And again, when you open the bracket, it pops up with helpful hints, just like Excel. So we can identify that we just need to provide that number. If we leave off the semicolon, that'll print straight away. If you wanted it to print a bit more nicely, you could put in like disp square root number, and that might neaten up the format a little bit. So then next we need to do our else statement. So if the condition is not met, display the message the square root is imaginary. That's the second like white dot point there. So disp the square root is imaginary, and we're not going to provide it in that case. So the next step is to try several values for number to check that your code is working. So let's start with the number 23 and have a look over here. So let's actually see if we can. No, I'll leave it separate. Cool. So the square root is real for that one, which is the value we were expecting. So if we give it -12, the square root is imaginary because it's now a negative number. We can also test it at the boundary point of 0. The square root is real and the square root of 0 is 0. We could also try a number that we know the square root of, like 36, and we can see there that we get our answer as well. So that's how you would write the code for that one.
Next up, we're going to have a look at switch statements. So switch statements are kind of an alternative way of doing conditional processing. They're not as common as ifs. They're not very widely used at all, really, but it is important to have seen them. So let's have a look at how we can translate this if statement into a switch statement. So let's have a look first at how this if statement's working. So we've got our variables, numerator and denominator, and we're saying if the denominator is not equal to 0, then calculate the result. And we've left off the semicolon, so the result will actually get printed. Otherwise, display cannot divide by 0. So if it is 0, then we want to display an error message saying that we can't divide by 0. So we want to convert this into a switch statement. And switch statements work by first setting up your variables. So we can do the same thing for our variables as the example code has. And then we want to switch based on one of the variables. So we can say switch denominator, because that's the variable that we're interested in this case. So then we can say we want the case where it's 0, in which case we're going to display that cannot divide by 0 message. So this says if the switch statement, if that variable that's being switched is equal to 0, then we run this code. So if it's basically saying if denominator is equal to 0, display this. So that's how it relates to the if statement here. And then for kind of the rest of the cases, we can use the otherwise statement. So otherwise is kind of like the else version. So if it's any other number, then we're going to just calculate the result. Numerator divide denominator. And then we have to end the switch statement the same way we end the if statement. So if we run this now and head over to Matlab, we should get an actual result. However, if I change denominator to 0, cannot divide by 0 will show. So it's a little bit different to the if statement in that you have to have exact cases. So in this case, we needed to check the exact case where it was equal to 0. We can't do things like range statements. So it's kind of used quite commonly in things like game menus where someone might be choosing from like play a new game, view high scores, exit the program kind of options. It's not super common in mathematical stuff because usually you're more looking at a range of values.
Part 6 asks us to have a look at the difference between assignment and equality checking. So assignment is where we set a variable to a value. And when we do that, we want to use a single equal sign. So this one here is the correct one. Part B of this one asks which of the following code snippets shows the correct usage of equality checking. Equality checking is when we check whether one value is equal to another value. In this case, that's a double equal sign. So this one would be the correct one. That one's checking if the number is equal to 0, whereas this one is setting number to 0. Exercise 7 is all about pseudocode. So there's this flowchart that's being developed, and our task is to convert it to pseudocode. So I'll actually do that in Matlab. I'll pop it back up here. So the pseudocode might look something like this. First, we're going to need to get student grade or enter student grade, perhaps, this simple program. Then our next step is going to be check if the student's grade is greater than or equal to 50. If the grade is greater than or equal to 50, display pass. If the grade is not greater than or equal to 50, display fail. And the way that you can then use this is to actually build your real code. So now that I've written this, I can go through and add in my real code. So enter student grade. Well, I might call that something like student grade and give it a value of let's say 76 for now. Check if the student's grade is greater than or equal to 50. So I can go to the next line and say if student grade is greater than or equal to 50. If it is, then display pass. So here I would write dis pass. And notice I'm using quotation marks for those messages. It's because those are a string type, which we covered in the Excel section. So same thing here. Those double quotation marks indicate a string. If the grade is not greater than or equal to 50, display fail. So here we'd want to put in our else and this fail. And then we just need to close our if statement. So we've used those sort of just plain English comments to build up our actual Matlab code. And now we can run it. And if we have a look over here, we can see that this student passes. And if I put in the lower grade, they fail. If I put one in on the cusp, they pass. So the importance of pseudocode, it's sort of twofold. Firstly, it's really handy for planning your code. So particularly while you're new programmers and you're still learning MATLAB and everything else, it can be really handy to write down what you want to do, even before you know how to do it. And it doesn't need to be line by line. Like this example, it is line by line, but you can put in less pseudocode. So, for example, if you're not quite sure how you would approach something, you can just say, this is what I want to do, and come back to it. The other benefit is that it doubles as comments. So if you write pseudocode that explains to yourself what you want to do, it's also going to be beneficial for someone else who's reading your code to understand what you're doing. Commenting is super important in the real world because if you're writing software, you're often going to be sharing that with other members of your team. Either that or, you know, other people might then take your package on and improve it if you've written a software package. So yeah, that's sharing. And also you're going to forget what you wrote. So if you write some magnificent software package in MATLAB and then you don't use it for 2 years, when you come back to it, you're going to have a really hard time deciphering what you wrote. So having comments there can really help for just ease of understanding your code, explaining your code to someone else. And it also makes it a lot easier for me to find you marks if I can understand why you've done something that you've done, particularly if it's sort of not, if it's a sort of alternative approach to what we've learned in class, for example. So make sure you comment, make sure you use pseudocode to plan. It's really, really important. So it's just that % sign to start a line that won't execute. And yeah, you can get started on your assignment as soon as you get it by just writing pseudocode. So this is a nice short video, mostly theory-based stuff. Next week's exercises have a lot more code, so I'll go through all of that in detail like I did with those couple of coding questions today. Until then, enjoy the rest of your week, and I'll see you soon.